Hello everyone. This video presents our research titled 3 Questions Concerning the Use of Large Language Models to Facilitate Mathematics Learning. Recently, many studies address math word problem solving. However, the human utility of the mathematics reasoning processes and the natural language explanations generated by models within educational settings is rarely discussed. Given the capability of LLMs to generate free text rationalization, we analyze the ability of LLMs to provide adaptive feedback by identifying errors within a student's math problem-solving process. 3 research questions are proposed. The first research question is, how can LLMs be utilized to assist students in learning mathematical problem-solving skills? Since exams are a common way for teachers to evaluate student learning progress, in this study, we focus on leveraging LLMs to equip students with the knowledge skills needed to solve math word problems. This is the scenario of an LLM applied in mathematics education. After a student responds to a question, the model determines whether the student's answer is correct or not. If the answer is incorrect, the system provides adaptive feedback and offering an explanation. The system can also provide a report to the teacher to monitor students' learning progress. So, the ability of LLMs to solve math word problems and to understand and explain equations is critical. Next, the second research question is, what is the problem-solving capability of LLMs in mathematical problems and their ability to explain the computational process? To answer the question, we evaluate the performance of LLM on the MathQA dataset. We choose the GPT 3.5 model as our target LLM. Based on the results, we observe that the calculation abilities of the GPT 3.5 model remain far from satisfactory. It frequently fails at simple arithmetic operations or counting. We invited an expert to evaluate the answers generated by the GPT 3.5 model. A total of 120 questions were selected by the expert. 10 error types are defined by the expert. We find that although GPT 3.5 is good at providing comprehensive explanations, its calculations are inconsistent, and the model often used incorrect formulas or methods to solve it. It still struggles at understanding the question. Finally, the third research question, are LLMs able to identify errors in students' answers and provide corresponding explanations? Due to the difficulty in obtaining real-world student answers, we simulate a scenario where students answer questions and the teacher corrects the students' answers. In other words, GPT 3.5 first acts as a student to answer the question. Then, it acts as a teacher to correct the problem-solving result. This table presents the results of the teacher-student framework. We compare the results with and without the question rationales. We find that if the corresponding rationales are not given as input, the accuracy of the model acting as a teacher to correct students' answers is lower than that when directly answering questions. Besides, if the corresponding rationales are given as input, accuracy is only 73.71%. So GPT 3.5 has difficulty understanding the equations given in the rationales. In conclusion, this work proposes a research agenda on using LLMs in mathematics learning. LLMs are limited in accurately identifying humans' errors. An advanced method is necessary. This is the end of my presentation. Thank you for your attention.